Hello, so today we are going to do problems from weekly contest, this week's weekly contest. And one of the problem is number of subarrays that match a pattern. So basically with this problem we have an array of size n, and we have another array pattern of size m, and pattern has only -1, 0, and 1. Okay, and we have a subarray from A from this array nums. We call a match with pattern if for index from I to j that has the same size as pattern plus 1, so m plus 1, if we have these three conditions, which is basically if the position for 0, for example, at pattern is equal to 1, then the number at position I plus 1 is bigger than number at position I. If pattern is 0, then that means it's equal. If the pattern is -1, that means the next one is smaller than the previous one. Okay, so basically the values in pattern tell us what should be the difference between each value and the next. Okay, and what we want to do is count the number of subarrays that match a pattern. Okay, so which basically means the number of subarrays that we can apply these conditions to. So that's the idea. And you can see here the constraints are very small. So that tells you can get away with just doing an O of n squared solution. And so what would be our O of n solution here? Well, it's pretty simple actually. What you can do is, well, if you have an array like this one, well, the easiest thing to do is just start I from here, and you are told that the array size is m plus 1. And so this is our number array, and we get a pattern array that we get, for example, in this specific case, it's 1, 1. And so we know m, which is the length of that array, is 2. So we know here the subarray has to be of length 2 plus 1. So it has to be of length 3. So in this case, we know that the subarray from this position 1, the only valid one is 1 to 3. So we can just take this one and check if these three conditions are valid, right? If they are valid, true, we count it. If not, we advance our I pointer. And so now we have a subarray, this one, and we check again. And we do the same thing until we traverse all the entire possible array, which basically means it doesn't make sense, for example, here to start I from 5, because then you don't have a full valid subarray. Okay, so that's pretty much is the approach here. So it should be pretty straightforward to implement. And so what do? Well, we need to go through the range of the length of nums. So let's call it n. Let's have two lengths, one for the length of the array and another one for the length of the pattern. And what we need to do now is we already know that we just need to check that the pattern is valid. So let's call that function check. So I, and what do we need to check? We need to check for each k in the pattern. So let's call it k, and we need to check for each k. And so in the range of m, so for the length. What do we need? Well, we need for all of these conditions to be valid for all k's. So we need all of them to be valid. If they are valid, then, so let's have a counter to count the number of subarrays that match. So let's call them matches. And let's start with 0. So let's actually change this to match. Okay, so if it does match, then if all of them match, then we can count, increase the matches by 1, and then at the end we return our matches. Okay, so pretty straightforward, but now we need to implement this match function. So it gets an I and a k, and we can actually just implement the exact conditions that we have here. Okay, and so that's what we'll do. We'll do something like this, except these ifs, we need to write them in a way that actually works. So if pattern is equal to 1, the value at the pattern, then we need to just return that it has to be bigger. If not, then there is no match. Same thing if the pattern is 0, it has to be equal. If it's not equal, then there is no match. So we return this. And similarly here, except here we can just do else, because we are told that pattern is either 1, 0, or -1. So in this case, we could just return that it's smaller, we don't need to check. Okay, so here we want to stop at n minus m, so that basically because we will do for the last k in this case would be m minus 1, okay? And so you can see here the last one here would be I plus k plus 1. This is the last one. Last position we'll check, okay? And so what this tells you basically is that if we do n minus 1, like this, then the last position is n minus m minus 1, okay? And this would be our last k, and we add this plus 1, so this would be the last I position, right? And this would be the last k position, and then if we do plus 1, overall this means basically we'll end up with, let's cancel things out, this one cancels out, this one cancels out, so the last position would be n minus 1, which is in bounds. But if we do n minus 1, m plus 1, then the last position for I is actually n minus m. And so what we'll end up with in that case is actually, let's cancel things out again. So what we'll end up with is, this is 0, this would be 0, so we'll end up with n, which is out of bounds. So we need to be careful there. So we should stop at n minus m, okay? And so if we run this, looks good, let's submit. And this passes, okay? Now, in terms of time complexity, this for loop here is O of n being the length of the array. This loop here is O of m. This is constant because it's only one check per if. And so overall, this is O of n m time, right? And in terms of space, it's we're not using really any extra space except this variable, so it's O of 1 space, okay? Yeah, and that's pretty much it for this problem. Thanks for watching, and see you on the next one.